Proxima Centauri, the closest star to Earth after our Sun, is 4 light-years away. Sounds close. But if you boarded the fastest spacecraft, Parker Solar Probe, screaming through space at over 400,000 miles per hour, it would still take 70,000 years to get there. We can see trillions of galaxies, their light arriving from a distant past, but there is an invisible wall between us and them. The speed of light, unbreakable, unless we don't move through space at all, unless space itself moves. If we can't break through the bars of the universe, what if we could bend the bars themselves? 1994. Miguel Alcubierre is watching Star Trek. The Enterprise goes to warp drive. Space bends around the ship, and suddenly they're crossing the galaxy in hours. Standard science fiction, right? The kind that ignores real physics. Except Alcubierre is a physicist who studies general relativity. He knows Einstein's equations inside and out. And watching that episode, he has a thought. What if this isn't pure fantasy? What if Einstein's equations don't actually forbid this? Here's what everyone knows about the cosmic speed limit. Nothing can move through space faster than light. 186,000 miles per second, fast enough to circle Earth 7 times in one heartbeat. Einstein proved this in 1905. The closer you get to light speed, the more energy you need to go faster. To actually reach light speed would require infinite energy. To exceed it, the math breaks down completely. This isn't a technology problem. It's built into how space-time works. The speed limit is absolute for anything moving through space. But, and here's the key, what about space itself? Einstein's general relativity says space isn't some fixed stage where events happen. Space is dynamic. It can curve, warp, even move. Mass bends space, that's what gravity is. Not an invisible force pulling things together, but curved space affecting how objects move. And space itself can expand or contract at any speed. No limit whatsoever. Right now, at this moment, there are galaxies at the edge of the observable universe moving away from us faster than light. Not because they're rocketing through space that fast, but because the space between us and them is expanding. The fabric of the universe is growing, stretching, carrying those galaxies along for the ride. Imagine you and a friend standing on a huge rubber sheet. Now imagine the sheet itself starts stretching. You're not walking. Your friend isn't walking, but the distance between you increases because the sheet is expanding. That's what's happening with distant galaxies. Space expands, they move apart, no speed limit violated. We measure this expansion. For every 3 million light-years of distance, space expands at an additional 43 miles per second. Doesn't sound like much, but at sufficient distances, say 10 billion light-years, that adds up to faster than light. Those galaxies aren't breaking any rules. They're just riding expanding space. And this isn't new. 0.4 of a second after the Big Bang, the universe underwent something called cosmic inflation. In less time than it takes light to cross an atom's width, space expanded by a factor larger than a trillion. The entire observable universe inflated from smaller than a grain of sand to larger than a galaxy in an instant, so brief we can barely conceive it. During inflation, space expanded way faster than light could ever travel through it. The universe violated its own speed limit on day one, has been doing it at cosmic scales ever since. Alcubierre realized this creates a loophole. If space naturally expands and contracts faster than light, if it does this routinely throughout cosmic history, why can't we make it do that locally? Why can't we create a bubble where space contracts ahead of a spaceship and expands behind it? He worked out the mathematics. Sat down with Einstein's field equations, the same equations that describe black holes, gravitational waves, how GPS satellites need timing corrections because they're farther from Earth's gravity. And he found a solution, a specific pattern of space-time curvature. Ahead of a spacecraft, space compresses. Distances shrink, 10 light-years becomes 1. Behind the spacecraft, space stretches. 1 light-year becomes 10. The ship sits right at the boundary between these regions, in a bubble of normal, flat space. This creates a wave in space-time itself. The bubble moves through space, carrying the ship along. From outside, the ship appears to travel faster than light. From inside, the ship isn't moving at all. It's just sitting there in its little bubble of normal space while the bubble itself surfs through the cosmos. Think of it like this. You're on a surfboard on the ocean. The surfboard isn't moving through the water faster than you could swim, but the wave beneath you is moving, carrying you along. The wave can move faster than you could ever swim because it's not an object moving through water. It's a moving distortion in the water itself. Warp drive is the same idea. The ship doesn't move through space faster than light. The ship barely moves at all. But the bubble of warped spacetime moves, carrying the ship with it. And bubbles of warped space aren't limited by the light speed restriction. Alcubierre published his paper in a physics journal. The warp drive, hyperfast travel within general relativity. The title alone was shocking. Here was a serious physicist using Einstein's own equations to show that faster-than-light travel might actually be possible. The physics community went crazy. Some looked for problems, ways the math might be wrong or physically impossible. Others looked for improvements, ways to optimize it, make it better, reduce the requirements, because there's always a catch. The catch is exotic matter. To bend space the way the warp drive requires, contracting it ahead, expanding it behind, you need something with negative energy, not just regular matter, something that pushes instead of pulls, gravity that repels instead of attracts. Everything we've ever encountered has normal gravity. Earth pulls you down. The sun pulls planets into orbit. Black holes pull so hard that light can't escape. Everything pulls. Negative energy would push, would create anti-gravity. It's like matter that falls up instead of down, that repels other matter instead of attracting it. We've never seen it, never detected it, never created it in any laboratory. It might not even exist. When Alcubierre first calculated how much exotic matter you'd need, the number was insane. To create a warp bubble big enough for a small spaceship, you'd need negative energy equivalent to Jupiter's entire mass. The biggest planet in our solar system, completely converted to this exotic stuff we've never seen. That wasn't just impractical, that was absurd. You'd have to sacrifice an entire planet for one spaceship to make one journey. But then in 2012, a NASA physicist named Harold White found ways to optimize the math. By changing the shape of the bubble, making it thicker, adjusting the geometry, he reduced the requirement dramatically. Instead of Jupiter's mass, you'd need about 700 kilograms. The weight of a small car, still exotic matter we don't have, still negative energy that might not exist. But the scale dropped from sacrifice a planet to maybe achievable with really advanced technology. In 18 years, just by refining the mathematics, the requirement dropped by a factor of trillions upon trillions. We went from completely impossible to merely extremely difficult. That tells us something important. The problem isn't necessarily that warp drive can't work. The problem is we don't know how to get the ingredients. And maybe we'll figure it out. Or maybe those ingredients simply don't exist, and warp drives remain forever theoretical. But here's what changed. We found the loophole. For a century, everyone thought the speed limit was absolute and unbreakable. Then Alcubierre showed us the fine print. The universe has a speed limit, yes, but only for things moving through space. Space itself can do whatever it wants. And if we're clever enough, if we can figure out how to manipulate space the way the universe does naturally during cosmic expansion, we might be able to use that loophole. The cage has a door. We found it. We can see it clearly. We know exactly how it opens. We just need to figure out if the handle is real or imaginary. Imagine you're at the beach, watching waves roll toward shore. The water rises and falls, moving toward the beach. Now imagine you're a surfer, sitting on your board. A wave approaches. The water beneath you rises, lifting you up. You feel yourself moving forward as the wave passes under you. You're not swimming. You're not paddling. The wave is carrying you. That's warp drive. You don't fight against space. You create a wave in space itself, and you ride it. But how do you make a wave in something you can't touch? How do you bend space? The answer is gravity, or More precisely, mass and energy bending spacetime. Picture a trampoline stretched tight and flat. Now place a bowling ball in the center. The trampoline sags, creating a depression around the ball. Roll a marble nearby, and it curves toward the bowling ball, rolling down the slope created by the depression. That's gravity. Mass curves space around it. Objects near that curved space follow the curves. They roll down the slopes. We call this gravitational attraction, but really, it's just objects following the bent geometry of space itself. Earth, sitting in space, creates a dip around it. We're all stuck in that dip. The sun creates a bigger dip. Planets orbit in that curve like marbles rolling around a bowl. Black holes create dips so steep that nothing can climb back out, not even light. All of this is passive. Mass sits there, bends space, and objects respond by following the curves. But what if you could actively push and pull on space? What if you could create curves on demand without needing massive objects? That's what exotic matter would let you do. Regular matter creates attractive curves, dips, and valleys that pull things in. Exotic matter would create repulsive curves, hills, and peaks that push things away. The warp drive uses exotic matter to create a very specific pattern. Not just a simple dip or hill, but a traveling wave. Space compresses ahead of your ship. Space expands behind your ship, and this pattern moves, carrying your ship along like a surfer on a wave. Here's how it works in detail. The exotic matter forms a shell around your spacecraft. Imagine a donut shape surrounding the ship completely. This shell creates the boundary between normal space inside and warped space outside. Inside the shell, inside the donut hole where your ship sits, space is completely normal, flat, regular. You could walk around, drink coffee. Everything behaves exactly like it does on Earth. Outside the shell, space is warped. Ahead of the ship, in your direction of travel, space is squeezed together like an accordion. Imagine a ruler that normally measures 1 foot. In compressed space, that same ruler would span 10 feet of distance. Space itself is scrunched up. Behind the ship, space is stretched out like taffy. That 1 foot ruler now spans only an inch. Space is pulled apart. Now here's the beautiful part. This isn't a static bubble, just sitting there. It's a dynamic wave that moves through space. The compressed region ahead and the expanded region behind create a slope. Like a hill, you can slide down, and the bubble slides down that slope, moving through space, carrying your ship inside. From your perspective on the ship, nothing weird is happening. You're in normal, flat space. Physics works normally. Gravity is normal, 1g. If you're using rotating sections for artificial gravity, time flows at regular speed. You could conduct any physics experiment and get exactly the results you'd expect in empty space, far from any stars. But from an outside perspective, your bubble is moving. Fast. Potentially way faster than light. And it can move that fast because the bubble isn't an object moving through space. It's a pattern of curved space propagating through flat background space. And patterns in space don't have speed limits. Think about ripples on a pond. When you drop a stone in water, ripples spread outward. The water itself isn't traveling horizontally. Water molecules just bob up and down, but the ripple pattern moves across the surface. Energy and information travel with the ripple, even though the water stays mostly in place. The warp bubble is similar. Background space isn't flowing, but a pattern of curvature is moving through it. Your ship, sitting in the flat region at the center of that pattern, gets carried along. The speed depends on how severely space is compressed ahead and expanded behind. With compression and expansion factors of 1000, you squeeze and stretch distances by a factor of 1000. A journey of 1000 light-years through normal space becomes effectively 1 light-year through the compressed space ahead of your bubble. So, how fast could you go? Theoretically, there's no upper limit. Want to cross the galaxy? 100,000 light-years in 1 week. That means your bubble needs to move at about 5 million times the speed of light. The math allows it. You'd just need enough exotic matter arranged in precisely the right pattern to create that much compression and expansion. Of course, we don't have any exotic matter at all, let alone tons of it in perfect geometric arrangements. But mathematically, arbitrarily high speeds are possible. From inside the ship, the journey duration depends on how fast your bubble moves. Cross 100,000 light-years at 5 million times light speed, and the trip takes 1 week. Your clock advances 7 days. You age 7 days. Time flows completely normally because you're in flat, normal space. This is radically different from conventional near-light speed travel. If you could somehow accelerate to 99% of light speed using regular rockets, time dilation kicks in. Time for you slows down relative to the outside universe. Travel for what feels like 1 year to you, and 7 years pass on Earth. Your friends age 7 years while you age 1. Get closer to light speed, say 99.99%, and it gets more extreme. 1 year for you, 70 years on Earth. You could leave for a long journey, experience just a few years, and return to find everyone you knew is dead and society has transformed. Warp drive eliminates this completely. Time flows the same for you and for Earth. Leave on Monday, arrive Friday, and it's Friday for everyone. No time displacement, no returning to find decades have passed. You stay synchronized with your civilization. That's huge for interstellar travel. With conventional relativistic speeds, you become disconnected from your society. With warp drive, you don't. But there are serious problems. First, what you'd see. Light traveling through warped space bends and distorts. At your bubble boundary, where space transitions from normal to severely curved, light rays bend extremely sharply. Looking out your windows, you wouldn't see normal stars. Stars ahead would appear compressed into a single brilliant blue point. Not because you're moving toward them, you're not moving, but because space ahead is compressed, and light traveling through compressed space has shorter wavelengths. Blue shifted by geometry, not motion. Stars behind would stretch into red smears. Space behind is expanded. Light waves are stretched. Wavelengths get longer. Red shifted by the expansion, the view would be spectacular, but completely distorted. You probably couldn't navigate by visual observation. The bubble boundary would warp images beyond recognition, like looking through an extremely powerful lens that bends everything into unrecognizable shapes. More importantly, you're cut off from the outside universe. This is fundamental to how warp drive works. Your bubble is moving faster than light relative to surrounding space. For information from outside to reach you inside the bubble, it would need to catch up with your moving bubble. But information, light, radio waves, anything, travels at maximum speed of light through space. It can't catch up if your bubble is moving faster than light. Same thing in reverse. Information from inside can't get out. Signals you broadcast would fall behind your bubble, unable to keep pace. You're isolated, completely cut off. No communication in or out. No way to receive updates. No way to detect what's happening outside. No way to call for help if something goes wrong. This means you must program your entire journey before you start. Calculate where your destination will be, accounting for how stars move during your trip. Set the trajectory. Once the bubble forms and starts moving, you're committed. No steering, no course corrections, no changes. If your math was wrong, if the star you're aiming for has moved more than you expected, or if there's an unexpected object in your path, you won't know until you arrive. You could emerge light years from where you intended. You could emerge inside a star's outer atmosphere. You could emerge in the path of an asteroid. You're flying blind, sealed in a bubble, trusting that your pre-flight calculations were accurate. And space isn't empty. The interstellar medium contains hydrogen atoms. 7-timesation. About 1 per cubic centimeter on average. Doesn't sound like much, but when you're traveling light years, it adds up. Over a 4 light-year journey to Proxima Centauri, your bubble plows through trillions upon trillions of hydrogen atoms. Those atoms can't enter your bubble. They'd need to exceed light speed to do so. So, they pile up at the front edge like snow piling up on a plow. When you arrive and shut down your warp drive, all that accumulated matter gets released. Hydrogen atoms, cosmic ray particles, dust. Everything that built up during your journey suddenly blasts forward in a concentrated beam. Physicists have calculated the energy involved. For a 4-light-year journey, you'd accumulate about 700 grams of hydrogen. When released, that creates a particle beam with energy comparable to a gamma-ray burst, one of the most powerful explosions in the universe. Point that at a planet and you sterilize the surface. Atmosphere ionizes. Surface gets bathed in lethal radiation. Any complex life dies within hours. Your arrival isn't gentle. It's a weapon, unintentional, but devastating. So you can't arrive close to inhabited worlds, can't drop out of warp near anything you don't want to destroy. You'd need to emerge far away, maybe several times the Earth-Sun distance. Let the particle blast dissipate harmlessly, then use conventional rockets for the final approach. That adds time. Maybe days of conventional travel after your warp journey, still vastly faster than conventional interstellar travel. But the constraints and complications keep piling up. There's also the stability problem. Maintaining that exotic matter shell in perfect geometric arrangement for hours or days requires incredibly precise control. Any fluctuation in the exotic matter distribution changes the bubble shape. Small fluctuations might be fixable. Large ones could destabilize the entire bubble. If the bubble collapses while you're traveling, space suddenly snaps back to normal. The compressed space ahead expands violently. The expanded space behind contracts. The ship gets whipped around by rapidly changing space-time geometry. Tidal forces could tear the vessel apart. Even if the structure holds, the crew would experience crushing accelerations that would kill them instantly. And the energy release from bubble collapse? Calculations suggest it might rival a supernova in localized intensity. All that warped space, suddenly equilibrating, releases enormous energy. Gravitational waves, radiation bursts. Anyone watching from light years away would see a flash. So warp travel, if possible, is dangerous. You're flying blind. Can't communicate. Can't change course. One malfunction and you're dead. Arrival creates deadly particle beams. The list of problems goes on, but if it works, if you solve all these issues, you could cross light years in days instead of millennia. You could visit other star systems within human lifetimes. You could explore the galaxy not as a multi-generational project, but as something individual humans might actually do. The mechanics work mathematically. Einstein's equations permit it. We understand how the bubble would function, how space would curve, how the ship would ride the wave. We just need exotic matter, which brings us back to the impossible ingredient. 700 kilograms of exotic matter. That's what the optimized warp drive design needs. 700 kilograms of something we've never seen, never created, never detected anywhere in the universe. To understand why this is such a monumental problem, imagine I told you to build a house, and the blueprints call for bricks made of solid light. Not bricks that glow, bricks literally made from light itself, hard and stackable. You'd say that's impossible. Light isn't a building material. It doesn't work that way. That's exotic matter. We need something that behaves opposite to everything we've ever encountered. Start with what we know. Every object you've ever touched has normal mass. Your body, this planet, the sun, distant galaxies, they all have positive mass, and positive mass creates normal gravity that pulls things together. Drop a ball and it falls down, pulled by Earth's gravity. The moon orbits Earth, pulled by gravity. Earth orbits the Sunday, galaxies pull on each other. Everything in the universe attracts everything else through gravity. This is so fundamental to our experience that it's hard to imagine anything different. Gravity always pulls, always attracts. Every massive object curves space in a way that draws other objects closer. Exotic matter would do the opposite. It would have negative mass, negative energy. Instead of creating an attractive gravity well, it would create a repulsive gravity hill. Instead of pulling things toward it, it would push them away. Drop a ball near negative mass, and the ball would fall up, pushed away by anti-gravity. Place negative mass near Earth, and Earth would accelerate away from it, not toward it. Gravitational repulsion instead of attraction. This has never been observed, ever, anywhere. We've studied neutron stars, where matter is compressed to nuclear densities. We've observed black holes where gravity is so intense that space-time itself is torn. We've examined the universe moments after the Big Bang when temperatures and energies were higher than anything since. And everywhere, every time, we find only normal positive mass creating normal attractive gravity. Never repulsion, never anti-gravity, never negative mass. Yet the warp drive equations absolutely require it, not as an optional enhancement, as a fundamental necessity. You cannot create the required space-time curvature pattern with only positive mass. To compress space ahead and expand it behind, you need negative energy density forming that shell around your ship. When Alcubierre first calculated the requirements, he found you'd need exotic matter with mass equivalent to Jupiter, the largest planet in our solar system, 300 times Earth's mass, completely converted to this stuff that might not exist. Jupiter has more mass than all other planets combined. Converting it to exotic matter for one spaceship is absurd. Even if you could do it, which you can't, you'd be destroying entire planetary systems for single journeys. Harold White's optimization in 2012 improved this dramatically. By adjusting the bubble's shape and thickness, he reduced the requirement to roughly 700 kilograms. About the mass of a small car, that's still 700 kilograms of something we've never produced. But the psychological difference is enormous. Jupiter's mass feels impossible. 700 kilograms feels like maybe, possibly, with really advanced future technology, we might manage it. If exotic matter exists at all, here's what we do know. Quantum mechanics predicts that empty space, vacuum, isn't truly empty. It's filled with quantum fluctuations. Particle pairs pop into existence for tiny fractions of a second, then disappear. An electron and its antimatter twin, a positron, appear briefly and annihilate. This happens everywhere, constantly, at scales too small to directly observe. These fluctuations create vacuum energy, normally positive, but in specific setups, you can create tiny regions where energy becomes temporarily negative. The Casimir effect demonstrates this. Take two flat metal plates in a vacuum, place them incredibly close together, nanometers apart, about 1/10,000th the width of a human hair. The plates restrict which quantum fluctuations can exist between them. Only certain wavelengths fit in that tiny gap. Outside the plates, all wavelengths contribute to quantum fluctuations. This creates an imbalance. Fewer fluctuations between the plates than outside. The energy density between the plates becomes slightly negative relative to the surrounding vacuum. And this creates a real, measurable force pushing the plates together. Hendrik Casimir predicted it in 1948 based on quantum theory. Experiments in the 1990s measured it precisely, confirming the prediction, so negative energy exists. We've proven it experimentally. But, and this is critical, the Casimir effect produces incredibly tiny amounts in incredibly tiny spaces for incredibly brief times. The gap must be nanometers wide. The force is less than the weight of a single grain of sand. The effect is measurable only on areas smaller than your fingernail. Warp drive needs 700 kilograms of exotic matter sustained continuously across a 10-meter bubble for hours or days of travel. Compare those scales. Casimir effect. Nanometer gaps. Forces measured in billionths of a Newton. Fingernail-sized areas. Warp drive. Meter-sized shell. Kilogram quantities. Continuous operation. That's a difference of roughly 30 orders of magnitude in size and 40 orders of magnitude in energy. It's like demonstrating you can light a match and claiming you can therefore melt continents. The question isn't whether negative energy exists. We know it does in tiny quantum amounts. The question is whether you can scale it up to macroscopic levels, and quantum physics might forbid that. There's something called the quantum interest conjecture. It says that if you borrow negative energy in one place or time, you must pay it back with extra positive energy somewhere else or later. Nature allows temporary negative energy but demands compensation with larger positive energy. Imagine your bank allows you to have a negative balance temporarily, but every dollar you go negative, you must eventually repay $2 positive. You can briefly dip into negative, but you can't stay there indefinitely, and you can't go deeply negative without owing massive positive balances later. If this conjecture is correct, and several quantum physics theorems support it, then large-scale, sustained exotic matter is impossible. You might create brief, small negative energies like the Casimir effect, but you can't maintain the continuous distributions warp drive requires. Some physicists think this is fundamental, that quantum mechanics has built-in safeguards preventing macroscopic negative energies, not because we haven't discovered how, but because nature forbids it at a deep level. Then there's dark energy. This mysterious stuff makes up about 70% of the universe and causes cosmic expansion to accelerate. We don't know what it is, but it behaves like it has negative pressure, pushing things apart instead of pulling them together. Some researchers wonder if dark energy might be related to exotic matter. If we could understand and harness it, maybe we could use it for warp drives. But we don't understand dark energy at all. We know it exists because we can see its effects, galaxies accelerating apart. But what it fundamentally is, complete mystery, and it's incredibly diffuse, spread uniformly throughout all space at extremely low density. Hoping dark energy solves our exotic matter problem is like saying we'll use that mysterious thing we don't understand and have never touched. It's not a plan. It's wishful thinking. Other ideas exist. Maybe string theory, if it's correct, permits exotic matter in certain configurations. Maybe quantum gravity effects at extremely small scales could produce it. Maybe there are production methods we haven't imagined, but string theory is unproven. We don't know if it describes reality. Quantum gravity remains an unsolved problem. We don't have a complete theory yet. We're speculating about speculative physics that might not be real. Here's the sobering part. If exotic matter could exist naturally, we'd expect to see it somewhere. The universe has had 13.8 billion years and countless extreme environments to produce it. Neutron stars compress matter to densities exceeding atomic nuclei. If extreme compression could create exotic matter, neutron stars should have it. We see no evidence of that. Black holes represent the most extreme gravitational environments possible. If extreme curvature could spontaneously produce exotic matter, it should show up around black holes. We see no evidence. The early universe, fractions of a second after the Big Bang, had energies and densities far exceeding anything since. If exotic matter could form under extreme conditions, it should have formed then. But cosmological observations show no exotic matter influencing how the universe evolved. Everywhere we look, every extreme environment, every epoch of cosmic history, we find only normal positive mass, never anti-gravity, never repulsion, never exotic matter. This absence is telling. It suggests exotic matter might not exist. That nature permits it only as microscopic quantum curiosity, not as macroscopic material you could engineer with. Maybe the Alcubierre warp drive is like a mathematical perpetual motion machine. The equations work. The math is self-consistent, but physical reality refuses to implement it. Not because the math is wrong, but because the ingredients it requires don't exist in our universe. We found the blueprint for faster-than-light travel. The blueprint is beautiful, elegant, based on Einstein's equations that have been tested and confirmed in countless other ways, but the blueprint calls for bricks made of solid light. And no matter how perfect the blueprint, if the materials don't exist, you can't build the house. Maybe future physics will reveal pathways to exotic matter we haven't imagined. Maybe some brilliant insight will show how to produce it, stabilize it, use it. Or maybe we'll prove definitively that it's impossible, that quantum mechanics absolutely forbids it beyond microscopic scales, that the door we found is painted on the wall, a perfect illusion with no actual opening. We won't know until we solve deeper physics problems, until we develop complete quantum gravity theory, until we understand whether the universe truly permits what the mathematics describe. That might take decades, might take centuries, might never happen. Meanwhile, we have 700 kilograms of impossible material standing between us and the stars. The door is there. We can see it, measure it, describe exactly how it opens. But the handle might be made of dreams. Let's dream for a moment. Let's say we solved it. Someone figured out how to create exotic matter, stabilize it, control it. We built an Alcubierre drive. You're standing in the control room of humanity's first warp-capable spacecraft. Engineers are running final checks. Your destination is programmed. Proxima Centauri, 4.2 light-years away. At conventional speeds, 70,000 years. With warp drive, if calculations are correct, maybe 36 hours. The exotic matter generators hum to life. You feel nothing. No vibration, no rumble. Just a subtle shift in the light outside the viewports. Stars ahead begin to compress. Their light shifts blue, not because you're moving toward them, but because space itself is contracting in that direction. Stars behind stretch and redden as space expands. The colors shift not from your motion, but from geometry itself changing. Then the bubble forms completely. You're now inside a 10-meter sphere of perfectly normal space, surrounded by a shell of exotic matter, creating impossible curvature outside. The boundary between your flat interior and the warped exterior is sharp, precise, maintained by exotic matter distributions controlled to within nanometers. And then you're moving. Except you're not. Stand up and you feel normal gravity, 1g from rotating sections. Walk around and everything behaves exactly as it should. Pour water from a glass and it flows normally. Drop a pen and it falls at exactly the rate you'd expect. Physics inside the bubble is completely ordinary. You're in flat, empty space as far as local physics is concerned. Time flows at normal speed. Your clock ticks regularly. You age normally. But outside, your bubble is sliding through space at speeds that would make light seem to crawl. From an external observer, if anyone could watch, they'd see something impossible. Your ship would shimmer briefly, then seem to vanish as the bubble detached from surrounding space. The bubble itself would shoot away faster than light could follow, leaving nothing behind. But you experience none of this. Inside your bubble, you're just sitting there, reading a book, drinking coffee, waiting. The journey to Proxima at this speed takes about a day and a half, 36 hours. During that time, you're completely cut off from the rest of the universe. Think about what this means. Right now, at this moment, Earth exists. People are living their lives, going about their day, but you can't know that. Information from Earth, radio signals, light, anything, can't catch up to your faster-than-light bubble. You're moving away from Earth faster than information can travel, and you can't send signals back. Any message you broadcast would fall behind your bubble, unable to keep pace. You're in a bubble of causality, a region of space-time temporarily disconnected from the rest of reality. It's like being in a soundproof room during an earthquake. The room is perfectly calm, perfectly quiet, but outside, the building might be collapsing, and you'd never know until you open the door. Except you can't open the door, not until you arrive. Your instruments show nothing outside the bubble. The severe curvature at the boundary bends light so dramatically that external images are distorted beyond recognition. Maybe you see patches of compressed stars ahead, smears of red behind, but clear images? Navigation by sight? Impossible. You programmed your destination before departure, calculated where Proxima Centauri would be 36 hours from now, accounting for its motion through space. Set the trajectory. Now you're committed. if your math was wrong, if Proxima moved differently than expected, or if there's an unseen companion star in your path, or if a rogue planet happens to be crossing your route, you won't know until arrival. You're flying blind through interstellar space at 1,000,000 times light speed, trusting calculations made days ago. And you're not alone in that space. The interstellar medium exists. Hydrogen atoms, cosmic rays, dust particles. On average, about 1 hydrogen atom per cubic centimeter. Doesn't sound like much, but you're crossing 4 light years. 4 light years is about 40 trillion kilometers. Your bubble has cross-section of maybe 100 square meters. In that volume over that distance, you encounter roughly a billion hydrogen atoms. Those atoms can't enter your bubble. They'd need to exceed light speed to match your bubble's motion, and they can't. So they accumulate at the forward boundary, piling up, building up, like snow accumulating on a plow blade. During your 36-hour journey, you collect about 700 grams of hydrogen at your bubble's leading edge, plus cosmic rays, plus any dust or larger particles in your path. 700 grams doesn't sound dangerous, but it's not just sitting there. It's compressed by the bubble boundary, energized by the interaction with your warp field. When you arrive and collapse the bubble, all that accumulated matter releases in a directed blast. Think of it like this. You're driving through a snowstorm. Snow accumulates on your windshield. Now imagine you're driving at 1,000,000 miles an hour and the snow is being compressed by the air pressure into solid ice. When you stop, all that compressed ice explodes forward with the energy it accumulated during your journey. Except instead of ice, it's hydrogen and cosmic rays. And instead of windshield pressure, it's space-time curvature. And the energy release is comparable to a gamma-ray burst. Gamma-ray bursts are the most energetic explosions in the universe after the Big Bang. For a few seconds, they can outshine entire galaxies. They release as much energy as the sun will emit over its entire 10 billion year life. Your warp arrival creates a miniature version of that, directed forward. Point that at a planet and you sterilize everything on the surface facing you. Atmosphere ionizes. Anything living gets hit with lethal radiation doses. The surface might actually glow from the energy deposition, so you can't arrive close to your destination, can't drop out of warp near Proxima Centauri's planets. You'd kill anything living there before you even said hello. You need to emerge far away, maybe 10 times the Earth-Sun distance out, far enough that the particle beam disperses into space harmlessly. Then you use conventional rockets for the final approach. That adds maybe a day of conventional travel. Still faster than 70,000 years. But your 36-hour warp journey just became 60 hours total when you include safe approach time. And that's assuming everything goes perfectly. What if it doesn't? What if the exotic matter generators fluctuate? What if the bubble geometry destabilizes? The bubble is maintained by precise exotic matter distributions. The shell around your ship has to have exactly the right density, exactly the right geometric pattern, exactly the right energy levels. Control systems monitor this constantly, making microsecond adjustments to keep everything stable. But what if something fails? A generator malfunction, a power fluctuation, a software glitch. The bubble starts to oscillate. The boundary between flat space inside and warped space outside begins fluctuating. Space around you is having a seizure, contracting, expanding, oscillating wildly. Inside, you'd feel it. Tidal forces. The front of your ship experiences different space-time curvature than the back. You're being stretched and compressed rhythmically as space itself vibrates around you. If it's mild, maybe control systems can stabilize it, compensate, bring the bubble back to equilibrium. If it's severe, the bubble collapses. Space snaps back to normal geometry violently. The compressed region ahead expands. The expanded region behind contracts. The ship gets whipped around as space-time oscillates back to flat. Tidal forces rip through the vessel. Metal screams. Structural members fail. The crew experiences acceleration forces that would turn them into paste against the walls. And the energy release, All that warped spacetime suddenly equilibrating creates an explosion. Gravitational waves propagate outward. Radiation bursts in all directions. From light years away, it would look like a supernova went off in empty space. Nothing inside survives. The ship is torn apart. The crew is killed instantly. And there's no warning, no time to react. One moment you're reading a book in your quarters. The next moment spacetime itself is tearing you apart. This is the nightmare scenario. And you can't prevent it from inside the bubble. You can't detect external conditions. Can't receive warnings. Can't know something's wrong until it's too late. You're committed to the journey, sealed inside. Hoping your calculations were right. Your equipment functions perfectly. And luck is on your side. Now imagine you make it. 36 hours pass. Your instruments show the bubble beginning its collapse sequence. Exotic matter generators start powering down. The warped space around you begins returning to normal. The blue compressed stars ahead rush back to normal colors and positions. The red stretched stars behind do the same. Images outside your viewport clarify as curvature decreases. And there it is, Proxima Centauri. A small, dim, red dwarf star, about 1/8 the sun's mass. Tiny compared to the sun you left behind. But you're here. You made it. The bubble collapses completely. The accumulated particles at your leading edge blast forward in a concentrated beam, shooting away from your ship at near light speed. Your instruments track it disappearing into deep space, far from any planets. No harm done. You're in normal space now. 4.2 light years from Earth. 36 hours after you left. Light from your departure won't reach Proxima for another 4 years. You beat it. You arrived before your own goodbye wave crossed the distance. Stand at the viewport and look back toward Earth. It's up there somewhere. A pale yellow star among thousands. Indistinguishable to the naked eye. Your home. Your family. Everyone you know. 4 light years away. But you crossed it in a day and a half. Here's the strange part. Back on Earth, it's been 36 hours. Same as for you. Your clock and Earth's clock are synchronized. You left Tuesday morning. It's now Wednesday night for both of you. This is completely different from relativistic travel. If you traveled at 99% light speed, time dilation would create massive differences. A few years for you, decades or centuries on Earth. You'd return to find everyone dead. Warp drive eliminates that. Time flows identically everywhere. You age 36 hours. Earth ages 36 hours. When you return, another 36-hour journey, you'll have been gone 3 days. Just 3 days for everyone. No temporal displacement. No returning to a transformed world. You stay synchronized with your civilization. That's the dream. That's what warp drive offers. Not just faster travel, but connected travel. You can explore the galaxy while remaining part of human society. You look out at Proxima Centauri and realize what you've done. You're the first human to visit another star system. The first to see another sun up close. The first to cross interstellar space within a human lifetime. You're farther from home than anyone has ever been. But you're not lost. Not displaced in time. Not cut off from your species. You're just elsewhere. And you can go back whenever you want. That's the beauty of it. That's what makes warp drive different from every other interstellar travel concept. But it requires exotic matter. It requires materials that might not exist. It requires solving problems we don't know how to solve. And it carries risks that might make it unusable even if we build it. You made it to Proxima, but your arrival nearly destroyed anything that might have been here. Your journey was a gamble with your life. Your technology requires impossible ingredients. The door opened. You walked through, but the price might be too high. You're in orbit around Proxima Centauri b, the potentially habitable planet circling the nearest star. Instruments are scanning. Initial readings show an atmosphere. Water vapor signatures. Possible biosignatures. This could be it. Another world with life. The first time humanity encounters biology that evolved independently of Earth. Then you notice something wrong. The atmospheric readings are changing. rapid ionization in the upper atmosphere, radiation levels spiking, energy deposition patterns spreading across the hemisphere facing your ship. You check the sensors again. The radiation is coming from the direction you approached from the path your warp bubble traveled. And you realize what happened. You thought you emerged far enough away. 10 times Earth-Sun distance seemed safe. The particle beam from your bubble collapse should have dispersed harmlessly into space. But you didn't account for the planet's position. Didn't realize Proxima b would be in the beam's path, even at that distance. Your calculations were off by a fraction of a degree, meaningless for most purposes, catastrophic for this. The particle beam, 700 grams of hydrogen and cosmic rays, accelerated to near light speeds, hit the planet's atmosphere. The upper atmosphere ionized instantly. Molecules ripped apart by high-energy particles. A column of superheated plasma formed where the beam struck. Shock waves propagated outward. Below, on the surface, anything in the impact zone was bathed in lethal radiation. Not just surface sterilizing. The beam penetrated deep. Ozone layers destroyed. Protective barriers against stellar UV radiation shredded. If there was life down there, complex multicellular organisms, maybe even something approaching intelligence, it's dying now. Radiation poisoning. DNA shattered. Cells unable to repair the damage. Your arrival just killed a world. Not intentionally. You took precautions. Emerged at what seemed like a safe distance. But the universe doesn't care about intentions. The physics of warp bubble collapse creates particle beams. Those beams carry enormous energy. And if anything is in their path, it gets hit. This is one of warp drive's darkest implications. Every journey creates a potential weapon. Every arrival releases concentrated energy. And you can't always predict where that energy will go. You can try to minimize it. Emerge farther away, maybe 100 times Earth-Sun distance instead of 10. Travel through less dense regions to accumulate fewer particles. Design bubble geometries that somehow capture and contain accumulated matter. But every solution adds complications. Emerging farther away means longer conventional travel times. Avoiding dense regions limits which routes you can take. Capturing particles while collapsing the bubble might be physically impossible given causality constraints. And even if you solve the accidental weapon problem, there's the deliberate weaponization concern. Military strategists would notice immediately. A warp-capable ship can arrive anywhere with a directed energy beam. Want to attack a planet? Warp near it, let your bubble collapse, and the particle beam does the work. You don't even need weapons on the ship. The warp drive itself is the weapon, and you could make it worse. Travel through a dense nebula before your attack. Accumulate kilograms of matter instead of grams. Create a particle beam powerful enough to crack continents. Imagine a warp ship deliberately routed through the Orion Nebula, 1,000 times denser than average interstellar space. A 4-light-year journey through that accumulates 10 kilograms of matter. When released, that's weapon-grade energy. Cities would be vaporized. Ecosystems devastated. A single warp ship could cause destruction exceeding nuclear arsenals. And there's almost no defense. The ship arrives faster than light. By the time you detect it, the beam has already been released. No time to evacuate, no time to raise shields, if such things existed, just sudden, devastating energy deposition. This creates profound ethical and political problems. Even if we solve the exotic matter issue, even if we build functioning warp drives, should we use them? Can we visit other star systems responsibly? Can we approach potentially inhabited worlds without risking their destruction? Can we trust our species with technology that turns every spacecraft into a potential superweapon? History doesn't encourage optimism. Humans have weaponized every powerful technology we've developed. Nuclear fission could power cities or destroy them. Chemical rockets could launch satellites or deliver warheads. Even the internet could connect humanity or enable surveillance and manipulation. Warp drives would be the same. Built for exploration, used for war. International treaties might help, The Outer Space Treaty of 1967 prohibits placing weapons of mass destruction in orbit and using celestial bodies for military purposes. We could extend that to warp drives, prohibit approaching inhabited systems, require emergence at minimum safe distances, ban military applications, but enforcement becomes impossible at interstellar distances. A ship could violate protocols light years away, and Earth wouldn't know for years. By the time information reached us, it would be far too late. You can't police the galaxy when information travels at light speed, but violations can happen faster. Then there's another issue, one that's more subtle but potentially more serious. Warp bubbles create gravitational waves. Moving that much warped spacetime through space generates ripples in geometry itself. Not gentle ripples like from orbiting black holes. Intense, localized distortions from rapidly moving curvature. These waves propagate outward at light speed. They're detectable. Our LIGO and Virgo gravitational wave detectors on Earth can sense black holes colliding billions of light years away. A warp bubble passing through nearby space would create signals orders of magnitude stronger. This means warp travel isn't stealthy. Your passage through a star system announces itself to anyone with gravitational wave detectors. They'd see you coming hours before you arrive. Plenty of time to detect your warp signature, calculate your trajectory, know you're approaching. For peaceful exploration, that's fine. But for military applications, it's problematic. You can't approach secretly. Any civilization advanced enough to detect gravitational waves, which means any civilization probably advanced enough to be interesting, would see you coming. But here's the flip side. Gravitational waves could be used for communication. You could modulate your warp bubble's geometry to encode messages. Those messages propagate at light speed, not faster, but they pass through matter with minimal interaction. Almost nothing blocks gravitational waves. This might be how advanced civilizations communicate. If they exist, if they've solved exotic matter and built warp drives. Which raises an uncomfortable question. Why don't we see them? We've been looking for signs of alien civilizations for decades. Radio telescopes scanning for signals, optical telescopes searching for megastructures, gravitational wave detectors measuring cosmic ripples. We've found nothing. No artificial radio signals, no signs of stellar engineering, no gravitational wave patterns matching warp drive signatures. Maybe exotic matter is impossible and no one has warp drives. Maybe civilizations exist but use different, faster-than-light methods, wormholes, dimensional shortcuts, something we haven't imagined. Maybe they're out there using warp drives, but too far away for us to detect yet. Maybe we're the first technological civilization in this region of the galaxy. Or maybe, and this is the dark interpretation, civilizations that develop warp drives destroy themselves with them. Maybe the weaponization potential is too great. Maybe the particle beam problem causes accidental genocides. Maybe the destabilization risks lead to catastrophic failures. Maybe warp drives are a filter, a technology that looks promising but actually prevents civilizations from spreading to the stars. We don't know. We're speculating about aliens we've never met using technology we can't build. What we do know is that warp drives, if possible, are dangerous. They're not clean solutions to interstellar travel. They're powerful, double-edged technologies that could enable exploration or enable destruction. Your ship is still in orbit around Proxima b. The radiation is settling. Atmospheric chemistry is stabilizing, though probably changed forever. Whatever might have been living down there is dying or dead. You came to explore, to discover, to represent humanity making peaceful contact with another world. Instead, your arrival was an attack, unintentional but devastating. And this is assuming you could even build the drive in the first place. Assuming exotic matter exists. Assuming you could solve all the technical challenges. Maybe it's better that we can't. Maybe the locked door should stay locked. Pull back now. Come back from Proxima Centauri. Back from imagined warp journeys and particle beams and exotic matter. Come back to Earth. You're here, right now, under familiar sky, the same stars humans have looked at for hundreds of thousands of years. Proxima Centauri is up there somewhere, You can't see it with naked eyes, too dim, but it's there, 4 light years away, along with hundreds of billions of other stars in our galaxy alone. And you still can't reach them, can't visit them, can't touch alien worlds or meet other forms of life if they exist. The cage is still locked, but something changed. You know about the loophole now. You know the speed limit isn't quite as absolute as it seemed. You know space itself can move faster than light, does so routinely, has been doing it since the universe began. You know we found a door in the wall, even if that door might be permanently locked, even if the key might not exist. We found it. And that matters. Think about what we did here. For a century, physicists believed the speed limit was unbreakable. Faster than light travel belonged in science fiction, alongside time machines and magic. It violated known physics. Couldn't happen. End of discussion. Then Alcubierre asked a different question. Not, can we move through space faster than light? But, can we make space move? And Einstein's own equations, the same equations that proved the speed limit exists, said yes. We didn't break the rules. We found the fine print. The universe has a speed limit for objects moving through space. But space itself? Space can do whatever it wants. It proved that during cosmic inflation, proves it now at the edges of the observable universe, where galaxies recede faster than light. The rules have an exception, and we found it. Maybe we never use it. Maybe exotic matter is fundamentally impossible. Maybe quantum mechanics absolutely forbids it beyond microscopic scales. Maybe we're stuck in this solar system forever, but we asked the question. We found the edge of the possible and pushed against it. That's fundamentally human. Looking at boundaries and asking, but what if? Seeing cages and immediately searching for exits. Every impossible thing we've achieved started with someone asking that question. In 1903, powered flight seemed impossible. Humans had tried for millennia. Built wings, towers to jump from, machines that crashed spectacularly. Everyone knew it couldn't be done. Then the Wright brothers flew for 12 seconds. Barely got off the ground, but they proved it was possible. 66 years later, one human lifetime, we walked on the moon. From 12 seconds of flight to leaving Earth entirely. That's the pattern. Impossible becomes difficult. Difficult becomes routine. What we can't imagine becomes what our children take for granted. Maybe warp drive follows that pattern. Maybe we're in the pre-Wright brothers phase. We have the concept. We know what we need. We're identifying obstacles and working on solutions. Maybe in 66 years, we'll have prototypes. Maybe someone born today will witness the first warp flight. Or maybe not. Maybe warp drive is genuinely different. Maybe it's like perpetual motion machines. Something that seems logically consistent until you examine physics closely. Then you realize nature forbids it absolutely. We won't know until we try. Until we search more thoroughly for exotic matter. Until we develop complete quantum gravity theory. Until we either find the solution or prove none exists. But the searching matters. The trying matters. Even if we fail, we learn. We push human knowledge forward. We understand the universe more deeply. And maybe we find something unexpected. That's what often happens when you push boundaries. You're looking for one thing and discover something else entirely. Fleming was trying to cure bacterial infections. Accidentally discovered penicillin. Penzias and Wilson were trying to eliminate noise from a radio telescope. Discovered the cosmic microwave background proving the Big Bang. The list goes on. Maybe searching for exotic matter leads us to breakthroughs in quantum mechanics. Maybe optimizing warp drive equations teaches us new physics. Maybe we never build a warp drive but learn something equally profound. Or maybe we do build one. Maybe the breakthrough comes from an unexpected direction. Maybe dark energy turns out to be harnessable. Maybe string theory is correct and provides pathways we haven't considered. Maybe some brilliant 20-year-old right now will have an insight that changes everything. We don't know. Can't know. The future is genuinely uncertain. What we do know is this. We're the species that found the loophole. That looked at the cosmic speed limit and found the exception. That mapped a route to the stars even if we can't walk it yet. We're prisoners who found the blueprint for escape. The blueprint might require imaginary materials. The door might stay locked forever. But we found it, and finding it changes us. We're not ignorant prisoners who don't know they're trapped. We're conscious of our limitations. We understand the cage's dimensions. We know the theoretical weak points. That consciousness, that awareness of limits combined with refusal to accept them, that's what drives human progress. 70,000 years ago, early humans looked at stars and wondered. They had no idea what stars were, no understanding of distances, no concept of the cosmic scale. Just wonder at points of light in the night sky. Now we know. We know stars are distant suns. We know some died long before humans existed. And we're seeing ancient light. We know galaxies contain hundreds of billions of stars, and the universe contains trillions of galaxies. We went from wonder to knowledge. And knowledge didn't diminish wonder. It amplified it. Knowing Proxima Centauri is 4 light years away doesn't make it less amazing. It makes it more so. Knowing we can't easily reach it doesn't stop us from trying. It makes us try harder. That's the human response to limitation. Not acceptance. Not resignation. But how do we overcome this? We're small, unimaginably small. Earth is a pale blue dot in an image taken from the edge of our solar system. Our solar system is invisible from most of our galaxy. Our galaxy is one among trillions. We're specks, temporary, fragile, a thin film of conscious matter on a small rock orbiting an average star in an unremarkable galaxy. But we're also the part of the universe that woke up. That became conscious. That started asking questions about itself. We're the universe examining itself, trying to understand itself, working out its own rules. And we found a loophole in those rules, a door in the cage, a theoretical path to the stars. Maybe we walk that path, maybe we don't. Maybe the door stays locked, maybe we find different doors. Either way, we're searching, pushing, refusing to accept limits without testing them. That's what makes us human. Not success, but striving. Not arriving, but journeying. Not knowing all the answers, but asking better questions. We found warp drive in Einstein's equations. We might never build one, might never touch exotic matter, might never cross light years in days. But we found the concept. We pushed physics to its edges and discovered something unexpected. We proved the cage isn't quite as solid as it seemed. And that gives us something precious. Not certainty of escape, but possibility, hope. A roadmap towards something extraordinary, even if we never complete the journey. You're sitting here on Earth, under stars you cannot touch, in a solar system you might never leave. But you know the door exists. You know the speed limit has exceptions. You know the universe itself shows us faster than light is possible. We just need to learn its tricks. Maybe we learn them, maybe we don't. But we're trying. And the trying, the refusal to accept impossibility without testing it, that's the most human thing we do. We're trapped in a beautiful cage, windows showing us 1 trillion galaxies, bars made of physics itself. But we found the door, even if it's locked, even if the key is imaginary. We found it, and that's enough to keep searching. You're here now, Earth, the same planet where humans evolved, built civilizations, looked up and wondered. Those stars are still there, still impossibly distant. Proxima Centauri is still 4 light years away. Andromeda is still 2.5 million light years distant. The cage is still locked. But close your eyes for a moment. Imagine standing in that spacecraft, the one that doesn't exist yet, might never exist. The exotic matter generators hum around you, technology we don't have, powered by materials we've never touched. The bubble forms. Space compresses ahead, expands behind. You're inside normal space, but that space is moving, carrying you forward on a wave of geometry itself. Stars blur past. Not because you're moving, you're perfectly still in your local bubble, but because space is flowing around you faster than light can cross it. 4 light years in 36 hours. A journey that should take 70,000 years, compressed into a day and a half. Not by breaking physics, but by finding the loophole. By convincing space itself to carry you, the bubble collapses. You arrive. Another star system, another world. 4 light years crossed. You look back toward Earth, a pale yellow star among thousands. Indistinguishable now. Home. 4 light years away. But you crossed it in the time it takes to spend a long weekend. You did the impossible by finding what was always possible. By reading the fine print in the universe's rules. Open your eyes. You're still here. Still on Earth. Still trapped. The warp drive is still theoretical. Still dependent on exotic matter that might not exist. The door is still locked, but you know it's there now. You know space can do impossible things. You know the universe left us a clue in Einstein's equations, a description of not just our prison, but our potential escape. Maybe we never build it. Maybe exotic matter is fundamentally forbidden. Maybe quantum mechanics absolutely prevents it. Maybe we're stuck here forever, bound to this solar system, watching distant galaxies recede beyond our reach. Or maybe not. Maybe in 50 years, someone makes a breakthrough, discovers a pathway to negative energy we never imagined, figures out how to produce it, stabilize it, use it. Maybe that person is already born. Maybe they're a child right now, looking up at stars, wondering what's out there. Maybe they'll be the one to turn the key. Maybe it takes 100 years, maybe 200, maybe it never happens. The universe doesn't adjust its physics to match our timelines, doesn't care about our ambitions. Either exotic matter exists or it doesn't. Either the door opens or it doesn't. But while we're waiting for answers, we can still imagine, can still calculate, can still push against the boundaries. Somewhere out there, right now, space is expanding faster than light. Galaxies are being carried apart on a wave of growing space-time. The universe is doing the impossible, casually, constantly, effortlessly. It's been doing this since the beginning. Since inflation expanded the universe from smaller than an atom to larger than a galaxy in a fraction of a second. Since the Big Bang created space itself, the universe knows how to break its own speed limit. Does it all the time. Shows us it's possible. We just need to learn how it does it. How to ask space nicely to carry us. How to create those waves of compression and expansion on demand instead of waiting for cosmic expansion. Maybe we learn, maybe we don't. But we found the equation that describes it. We mapped the mechanism. We know what we need. We just need to find it. Or prove it doesn't exist. Until then, you're here, under these stars, in this cage with windows showing you everything you cannot touch. But you're also here knowing you're part of the species that found the door, that drew the map, that looked at absolute limits and found the exception. You're trapped. But you're the kind of trapped that understands the trap, that searches for exits, that refuses to stop asking what if. Maybe that's more important than escaping. Maybe being the kind of creature that dreams of warp drives matters more than building them. Maybe consciousness, this awareness of limitation combined with imagination of transcendence. Maybe that's the real gift. You're small, impossibly small, a pale blue dot in infinite cosmos, but you're also the part of the universe that woke up, that looked around, that started questioning its own nature. You're the universe examining itself, understanding itself, trying to escape its own limitations. And you found a door, even if it's locked, even if the key is made of impossible materials. Even if you never open it, you found it. The stars are still impossibly far. You still can't touch them, but you can imagine surfing space itself, riding waves of compressed and expanded geometry, crossing light years in hours, arriving before light can follow. You can imagine the impossible. And imagination, that refusal to accept cages without questioning them, that's the most human thing there is. Sleep now, under stars you cannot reach, in a cage you cannot open, but dream of warp drives, dream of exotic matter, dream of the day we find the key, or prove it was always imaginary. Dream of surfing through the cosmos, of touching alien worlds, of seeing suns no human has seen. Dream of the impossible. Because you're the species that makes impossible things possible. One calculation at a time, one discovery at a time, one dream at a time. The universe left us a clue. We found it.